Welcome back to The Explainer. Today, we're jumping straight into a rigorous university-level masterclass prepared by Dr. Nima Mahdian. If you've ever wanted to truly grasp the physical reality behind control theory, you are in the exact right place. We're going to synthesize passive controllers step by step, exactly as they're laid out in the textbook. We'll start with the foundational, elemental components and mathematically build our way all the way up to a full proportional integral derivative, or PID, system. So grab your notebooks. We're going to unpack every single concept, equation, and circuit right here without skipping a beat.
Here's the roadmap for today's session. We'll kick things off with an introduction to passive controllers. From there, we move to the elemental components. Then we step it up to first-level hybrid fusions, and finally, we'll cap it all off with full PID synthesis.
All right, let's get into part one, Introduction to Passive Controllers. Okay, let's dive into this. You know, when you study control systems, it's incredibly easy to get lost in the abstract math. But today, we're grounding all that theory in cold, hard physical reality. What we're looking at is a real FR4 printed circuit board. The complex transfer functions we're going to derive today actually exist right here in physical space, using standard off-the-shelf industrial resistors and capacitors. You can literally see the equation mapping directly to the physical hardware. H of S equals V out of S over V in of S, which equals R2 over the quantity R1 plus R2 plus 1 over SC. We aren't just doing math on a whiteboard today, we're talking about real physical hardware. Moving right along to section 2, the elemental components. First up on the bench is the proportional element. Physically, this controller is implemented using a super simple voltage divider. We've got our input voltage, VI, going through a variable resistor or potentiometer that's split into R and R1. The transfer function, K of S, is just VO of S over VI of S, which equals R1 over R. But hey, take a really close look at that physical constraint box at the bottom. Notice how the gain, K, is inherently limited? It strictly has to be less than or equal to 1. Why is that? Well, because a passive circuit has absolutely no external power source. It can only attenuate the input signal. It literally can never amplify it. Next in line, we have the integral element. This is your standard RC circuit. We have a resistor R in series, followed by a capacitor C tied straight to ground. Let's walk through the math here. The exact transfer function is VO of S over VI of S equals 1 over the quantity 1 plus RCS. But to make this act like a true integrator, we need to look at the approximated transfer function, which simplifies down to 1 over RCS. That gives us our integral time constant, Ti, equal to R times C. Now, how do we jump from the exact function to the approximated one? Check out the integration condition box. RC must be significantly greater than 1. For this thing to exhibit true mathematical integration behavior, that time constant has to be way larger than the period of the input signal. Finally, let's look at the derivative element. Notice what just happened here? We simply swapped the component topology. Now, the capacitor C is sitting in series, and the resistor R goes to ground. By doing this, the circuit reacts exclusively to the rate of change of the input signal. The exact transfer function becomes RCS over the quantity 1 plus RCS. And once again, we can approximate this to simply RCS, which makes our derivative time constant TD equal to R times C. But, and this is a big but, this requires us to respect a golden rule of engineering, shown right there in the differentiation condition. RC must be much, much less than 1. The time constant has to be highly responsive, meaning very small, so it can successfully capture those instantaneous signal variations. All right, section 3, first-level hybrid fusions. Let's move to and see how this builds our first fusion, the PI controller. By taking that isolated proportional voltage divider and our integral RC network and smashing them together, we construct the hybrid circuit you see in the middle. We've got resistor R in series, and then resistor R1 and capacitor C in parallel to ground. The exact transfer function now gets a bit chunkier. It becomes VO of S over VI of S equals 1 plus R1CS, all over 1 plus the quantity R times C plus R1 times C times S. If we apply our approximations, it shakes out to R1 over the quantity R plus R1 plus 1 over the quantity R plus R1 times CS. This perfectly isolates our gain K and our integral time constant Ti. Now, before we look at the final parameters for that PI controller, I want to give your brain a quick breather from the dense math. We need to explicitly define an essential engineering rule that you just saw hinted at. It's called the decoupling constraint, or sometimes the isolation constraint. This is a non-negotiable, strict design rule that requires one resistance to be significantly larger than another, for instance R being much, much greater than R1. And why is this so absolutely crucial? Because when you cascade passive stages, they essentially drain energy from one another. This constraint prevents that interactive loading between the stages, which ensures that our beautiful mathematical approximations actually hold up in the real physical world. And this brilliantly illustrates exactly how that constraint is applied. Here is our second fusion, the PD controller. We're fusing a high-pass derivative network, that's the parallel C and R block, with proportional attenuation via R1 to ground. The exact equation is R1 times the quantity 1 plus RCS all over R plus R1 times the quantity 1 plus RCS. Now let's apply that decoupling constraint we just talked about. R must be significantly greater than R1. When we do that, the R in the denominator completely dominates, the R1 term practically drops out, and we're left with our final approximated parameters. Gain K equals R1 over R, and our derivative time constant TD equals R times C. Just like that, we've achieved predictive control characteristics using purely passive components. Which brings us to our final section, full PID synthesis. Okay, let's methodically step through the climax of this lecture. Here is our third fusion, the PID controller. The circuit board now features resistor R1 in parallel with capacitor C1, which feeds into resistor R2 in series with capacitor C2 going to ground. Let's look at the exact transfer function, and don't worry, we aren't skipping a single variable here. H of S equals the quantity 1 plus SR1C1 times the quantity 1 plus SR2C2. All of that is over 1 plus S times the quantity R1C1 plus R2C2 plus R2C1 plus S squared times the quantity R1C1 R2C2. I know, it looks super intimidating, right? But honestly, it's just the mathematical reality of cascading the PD and PI sections that we've already mastered. So, the crucial point is, how do we make that massive equation actually useful for us? Well, we apply the grand engineering constraints for full PID synthesis. To make the exact function match our ideal PID transfer function, we have to physically enforce two specific rules. First, R1 must be significantly greater than R2. Second, the product of R1 and C2 must be significantly greater than 1. When you physically build your board with these exact constraints in place, everything collapses beautifully into the ideal approximated parameters for a PID system. Your gain K becomes R2 over R1, your derivative time constant TD becomes R1 times C1, and your integral time constant TI becomes R1 times C2. You now know exactly how to physically implement a full PID controller using nothing but resistors and capacitors. It's pretty amazing, right? But I want to leave you pondering this physical reality. While passive PID controllers offer incredible simplicity, exceptional reliability, and require absolutely zero external power source, what performance trade-offs must we accept by operating strictly with a gain of less than 1? If you can never, ever amplify the signal, how does that limit your control over a massive industrial system? Think about it. Thank you so much for joining me for this masterclass on the Explainer. Keep learning, keep analyzing, and I'll catch you next time.